I will continue talking about soil properties by focusing on really the most important thing to know is volume change response or volume change response tendencies to drain to shear. So volume change response in drain shear provides incredible insight for soil response in drain as well as undrained shear. And I'll talk about dynamic shear strength. Let's start with a simple triaxial test, a monotonic loading, and we're going to do drain loading to measure volume change tendencies. We're going to start with two tests at the same confining pressure, same soil. One has a high void ratio, one has a low void ratio. Void ratio is useful. The volume of the voids divided by the volume of the solids. It's very important in terms of giving us a sense of the state of the soil. But it is more important, it's more informative if we use the term relative density, where we take the Emax minus the void ratio normal divided by the void ratio difference. And so we have obviously a relative density of 0% to 100%, and it gives us more insight into just void ratio. Relative density is difficult to estimate in the field. At least with the compaction test, there's a very nice correlation that was developed by Lee and Singh in '71 that tells us relative compaction, the dry unit weight divided by the maximum dry unit weight achievable in a modified Proctor test, relative compaction minus 80% times 5 gives you an index or an indication of relative density. That's important because if you take a sandy soil and compact it to at least 90% of the modified Proctor maximum dry unit weight, that's only a relative density of 50%. When we talk about liquefaction, you're going to see that you want to compact the soil to at least a relative density of 75 to 80%. So now you're talking a relative compaction of potentially 96% of the modified Proctor maximum dry unit weight. When we perform this test, a soil that is contractive in drain shear is going to reduce in void ratio. The soil that has this loose configuration to shear, the particles will then move into the voids between the particles, and you will get a denser and denser soil as you shear it. If we have a soil that's already dense, it will initially contract, which is very important. Even a dense soil, when you initially shear it, will initially contract, but then, just like my knuckles, if I'm able to shear them without breaking my knuckles, and we don't typically get particle breakage at low confining pressures, I have to have them ride over each other. I have to have dilation. And so I get dilation, but then I get to a point where I'm at the same void ratio. No matter what void ratio I started at, when I do this test on this soil at constant effective stress, I will get to a critical void ratio where the soil will neither want to contract nor dilate with additional shear. If I do this test at a higher confining pressure, let's say 300 kPa, the soil that's contractive will be more contractive, and the soil that's dilative will be less dilative. So we have this idea that soil response depends on the void ratio or relative density, but it also depends on confining pressure. If I take the critical void ratio that I eventually get to in drain shear at each confining pressure, I can develop a critical state line. This is informative because we have void ratio and effective stress, and we're looking at the combinations of void ratio and confining pressures that soil will eventually get to in drain shear. If I know where you're at now, you're in Bogota, and I know where you die, The rest is just details. If you know where soil is now, and you know where it's going to get, the rest is details. The details are important. I'm trying to be a little humorous after lunch. But knowing where something's going to go eventually is an incredibly powerful framework for understanding soil response. There are three worlds in soil. There is being on the critical state. I could have a soil that just happens to be at critical state, and it will just stay the same void ratio and drain shear. But then I can have a soil that's above the critical state line, where it's contractive, and I can have a soil that is on the other side, the dilative side. It will contract a little bit, and it has to go to the critical state line. If I start here, and I know I'm doing a drained triaxial test at constant confining pressure, the only way you can get from where it's at now to where it has to get to eventually is to contract it a little bit and go back up to the critical state line, so I know it has to dilate. If I have a soil at the same void ratio or the same relative density, I should not be using the terms loose and dense, because it depends. I could have a soil that is dilative at a low confining pressure, and that same soil could be contractive at a high confining pressure. So we really should be thinking about void ratio or relative density and effective stress as a combination in terms of soil response as being primarily contractive in drain shear or primarily dilative in drain shear. Soils, like many materials, when you apply an isotropic stress to it, it will compress. What makes soils so interesting is you can just apply a shear stress and it will actually change in volume. So one of the most important concepts in soil mechanics is the dilatancy rule. The fact that soils change in volume. Get highly contractive, slightly dilative, highly dilative, and drain shear. This dilatancy concept is one of the most important concepts, but it can be demonstrated with just your knuckles in terms of basically contraction to shear, or if you're in a dense state, dilating to shear. If I look at a soil that's at a low confining pressure, at a relatively high effective stress, we're going to call that the loose sand. And if I have a soil that is under a very, very high relative density, or it's a low void ratio, and it's under an intermediate to low confining pressure, it will respond as the dense sand. You can see the volume change tendency. So this is contraction, a reduction in void ratio. This is dilation. This is axial strain. If we shear these boxes, initially both of them will contract a bit. The loose soil will contract more. The dense soil and loose soils both reach contraction. They're both going down in terms of void ratio. They both basically have a contractive volumetric strain. We get to a point where the dilative soil has to dilate to allow the shear between the grains to occur. And actually, when we get to the maximum rate of dilation, which is the slope of this curve of volumetric strain versus axial strain, we get to the greatest ability to carry stress, or the peak strength. The contractive soil continues to contract, so the contractive soil is getting denser as I shear it, so I should expect a strain hardening kind of response. The dilative soil is actually dilating, it's doing work against an applied stress field, right, it's peak strength, but then that work starts to slow down, and you can see that we eventually get to critical state. If we look at a dense soil, a soil that wants to be dilative given its void ratio and its effective stress, it will initially contract in drain shear, but then it has to dilate to allow the shear to happen. Where that dilation occurs is the phase transformation line. That's a critical concept, that when you go from contractive tendencies in drain shear to dilative tendencies in drain shear, you're crossing the phase transformation line. Then the soil will dilate. It will dilate at a fast rate, but then it will eventually slow the rate of dilation. And at that applied stress, it will reach the critical void ratio for that applied stress, or the critical void ratio. So one of the key aspects of this framework is this concept of a critical state, or sometimes in undrained shear we call it a steady state of deformation. The critical state definition is eventually, if I load the soil to enough strain and let it get to its happy place, where it wants to go, it will have stationary effective stresses. The mean effective stress, sigma prime 1 plus sigma prime 2 plus sigma prime 3 divided by 3, will be, as I increase the shear strain, will be 0. The change in the rate of the applied deviator stress, sigma 1 minus sigma 3, or sigma 1 prime minus sigma 3 prime, will be 0 with increasing shear strain. And the volumetric strain increment divided by the shear strain increment will be 0. Now, this is a framework. Like any theory or framework, it's what we expect the soil to do is idealized. As you get to natural soils with structure and fabric, you may see some deviations from this. The other important point I wanted to make was when you have the maximum rate of dilation, the maximum slope of the volumetric strain versus axial strain plot is when you get to the peak strength. Many times in statics, we want to have factors of safety. We're dealing in this world, so we only think about peak friction angle. But in earthquake engineering, we often go beyond peak, and so we want to know what the peak is as well as what the steady state strength is. This is one of the best data sets for exploring this. Lee and Singh did some phenomenal testing. This was done on Sacramento sand in the 60s and published in 67. This is as presented in the Idris and Boulanger book in 2008. But you can see two cases here. You have the same soil, and what they decided to do is they took the soil and built the specimens with a relative density of 100%, and they built the specimens with a relative density of 38%. They went over a wide range of stresses from 1 atmosphere to 116 atmospheres. So a large range of stresses. As a structural engineer who turned to geotech, I always want to look at strength first. I've learned I was wrong. You really want to look at volume change tendency first. If you understand volume change tendency, then you understand the stress-strain relationship. So, for example, even at 100% relative density, under such a high consolidation stress, the soil is contractive in drain shear, and therefore it has a strain hardening response. It's looking like the loose sand response that I talked about. Under low confining pressures, it barely contracts and it rapidly dilates and then reaches critical state void ratio. That rapid dilation leads to the highest peak strength and also the biggest drop in the post-peak strength regime. And then the other cases are intermediate, where we might get some contraction and a little bit of dilation, and we get basically both a peak and then a drop in strength. This is on the same soil, same series of testing, but it's under relative density of 38%, something we would consider loose, and you can see that under the high confining pressures, it is very contracted. It's more contracted than it was at 100% relative density. And even at this low relative density, under low confining pressures, it contracts a little bit, but then it dilates a little bit. And that little bit of dilation is making that little bit of the peak strength before it drops back down to the critical friction angle strength. Please spend some time studying these diagrams and seeing if you can draw them on a blank piece of paper, because then you understand some of the key aspects in terms of relative density and confining pressure and their impact on volume change tendencies during drain shear. But we want to start talking cyclic. This is a nice series of tests done by Les Youd, where he's looking at volume change tendency during drain cyclic shear. He initially built the specimen with a relatively high relative density of almost 80%. You can see how it contracts because void ratio is going down, but then it crosses the phase transformation line and then dilates, contracts, dilates, contracts, dilates. A lot of volume change in the first few cycles. You can see you have to skip way ahead, and he's omitting a lot of cycles in between. But at the bottom, you are working that soil, you're probably getting some particle breakage, and you are continuing to get contraction and then dilation, but you're getting less contraction and more dilation each cycle, and it takes a lot of cycles to get down this curve. You end up with a relative density greater than 100%, which reminds you that Emax and Emin, and hence relative density, is an index. We have standards to develop the maximum void ratio by a laboratory procedure and the minimum void ratio by a laboratory procedure, but that's not the maximum void ratio or minimum void ratio you can achieve in the field. Why volume change tendencies are so important, whether a soil is contracted in drain shear or contracted and then dilative, is if you understand that, you understand pore pressure generation. If you understand how water pressure changes, you understand how effective stress changes. If you understand effective stress, you understand stiffness and strength. Because soil response is a function of effective stress. In fact, in the early days, they didn't have the capacity to do a cyclic undrained test, so they did cyclic drain tests, and they actually took the volume change tendencies and then computed what the water pressures would be. Now we can do fully drained tests, and when we do it, we find that that is consistent. A contractive soil will generate positive pore pressure. A dilated soil will develop positive pore pressures, but then we'll get dilation. And I'll say dilation. Obviously, if it's a constant volume test, it's fully saturated with water, it can't dilate. It wants to dilate. If you suppress the ability for soil to change in volume, it will be expressed in terms of pore pressure. So going back to what we looked at before, a dilative soil will have to get to the critical state line. If it's a constant volume test with a saturated specimen, and the water is relatively incompressible, the solids are incompressible, the only way it can get to where it is, to the critical state line or the steady state line, is at constant volume. So I know if I'm here, the only way I can go on an undrained test on a saturated specimen is to go this way. That causes the effective stress to increase because I'm getting a negative excess pore pressure. What should scare us more is this point where the soil is at some state. If I did drain shear, it would go this way. But if I constrain it with a rapid loading of a fully saturated specimen so that it's undrained, constant volume, constant void ratio, the only way it gets from where it is to where it wants to go is to go horizontally to the left, which means the pore pressures are building up, the effective stress is going down. So if we look at the drain test to the left, and we look at the undrained test to the right, if we look at volume change tendencies to the left, and pore pressure generation to the right, we see that they're connected. A soil would like to contract and drain shear. If it's loose, it would like to keep on contracting. That increase in tendency to want to contract is going to lead to an increase in pore pressure until I get to steady state where everything's stabilized. This is another important lab set. Professor Ishihara, working I think principally with the work of Ramon Verdugo, published a very nice piece of work where he looked at monotonic undrained triaxial compression tests. Again, I tend to want to move up here and look at this, but to understand it, you have to come down here and say, okay, this soil is consolidated to a high confining pressure. It only has a relative density of 18%. So we would expect it to primarily be contractive at most effective stresses, highly contractive under high confining pressures. What we find is it moves and it gets to the steady state line and then gets to the steady state line. This is actually a 3D diagram. We're just looking at a projection on a horizontal plane. So it doesn't actually cross over. It just moves above and then comes back to steady state. What Professor Ishihara realized is there's something called a quasi-steady state, which is a function of fabric. Yes, it's true that soil will eventually, if sheared, get to the steady state line. But it takes a detour, depending on fabric, and it goes to that quasi-steady state line and then gets to steady state. Why that's important is this soil building up its positive pore pressure moves, the effective stress moves to the left. So when you see a stress path, Q versus P prime, where the P prime is moving to the left, that's because you're building up water pressure. It hits its peak strength and it drops rapidly down to the quasi-steady state line, and then it does want to dilate a bit to get to its final place. In terms of stress strain, it's a very stiff response initially, up until peak, but then it rapidly falls down to the quasi-steady state strength. Why this quasi-steady state strength is so important is the soil may start to break apart and fail well before it can stay coherently together and get to steady state. So as a practical engineer, this plateau right here might be really what you have to focus on. In a laboratory test, I'm constraining the element of soil to stay together. In a real project, once I get out to this larger strain, I might start having things falling apart, and I might want to use a strength based on the quasi-steady state. This is geometrically similar, but because it's loaded to a lower confining pressure, it doesn't contract as much, it doesn't drop as much to the quasi-steady state, it doesn't have to move as far over, and then it doesn't have to dilate as much to get to steady state. And so you tend to get a strength that looks more like this. And again, this might be the operating strength of this material, because you may not be able to keep it together to have it dilate to get to this strength. So there is a critical state line and steady state line that are pretty close to each other. There's some nuances that need to be talked about, but I think more important is the quasi-steady state line, whereas the steady state or critical state lines are not a function of the fabric of the soil. However the soil started, given a confining pressure and given the void ratio, it gets to that critical state line, and it's just a function of how it gets there, whether it's a drained or undrained test. But the quasi-steady state line is actually a function of fabric, whether that soil has been deposited through pluviation through air, pluviation through water, or compacted in place. So density is one of the most important aspects, and we know that soil response is stress dependent. So whether a soil is loose or dense, whether it's contracted or dilated, depends on its initial state, but also its confining pressure. But we could have soils that are exactly the same void ratio, exactly the same effective stress, that have different fabric, because nature has built them differently. And you can look and see just with your eyeball that this soil is going to be more contracted. In the end, we're looking at some of the key aspects, but what the soil cares about is, given its fabric, given its particle arrangement, given the angularity of the particles, if you tried to do a drain test on it, would it be contractive, moderately contractive, or highly contractive? Or would it be dilative? Those things tell you whether it's a dangerous material during an earthquake loading, a highly contractive soil, because of fabric and density and effective stress, is going to generate more pore pressure than the soil that's not as contracted. So density and fabric depend on the current stresses, and they also depend on the depositional process and the stress history, which you clearly see affects the quasi-steady state line. Professor Kramer mentions the threshold strain concept. I think this is very useful to realize that soil goes from very small strains that are nearly linear elastic to small strain regime where things are nonlinear and elastic. There's negligible plastic strains. And then where we often live in the world of earthquakes is moderate to large strains where things are highly nonlinear, elastoplastic. In a drain test, we would get volumetric irrecoverable strains, and in an undrained test, we might get pore pressure generation. And unfortunately, there are cases where we get to very large strains that lead to failure. So this work by Thucydides that was published in 1994, which builds on the work of Ricardo Dobry and Ladd, is very informative for looking at the different strain ranges. In terms of GOG max, where we have largely a linear elastic range, but more important is this dividing line between when you get a little bit of nonlinearity and maybe a little bit of plasticity, but so small we can ignore it, to crossing the volumetric threshold strain, and we start to get large elastoplastic, a large plastic behavior, large irrecoverable strains. You can see the tremendous softening of the material as the void ratio reduces, and the opposite effect is for the damping. The volumetric threshold strain for a lot of clean sands is around 10 to the minus 2% shear strain. The last thing I'd like to talk about is dynamic strengths of clays. And for this framework, I'm using a paper that was published about 13 years ago. And we're going to focus first on peak dynamic shear strength. If you're working on a project and you need to come up with the peak dynamic strength, the most important thing to do is the peak static strength. I was working as a peer reviewer on a project with Jim Mitchell and Ed Idris. We had 8 hours. We could spend time on this topic, reviewing the work by others. We spent 7 hours talking about all the things that were actually talked about a little bit with the laboratory tests. Anisotropic formation of the soil, stress anisotropic, the strain rate effects, all of the stress history, whether it was normally consolidated, under-consolidated, slightly over-consolidated. We spent 7 hours coming up and saying, yes, this is the peak static strength. Then, in the spatial variability, both in the horizontal and vertical direction, and then and only then did we spend an hour talking about how to adjust that peak static strength for things such as rate effects of earthquake loading versus slow monotonic loading in the field, cyclic degradation issues, progressive failure, and cyclic or deformation or distributed deformation. So, rate effects. You have clays here. You're aware that clays are rate dependent. The strength, the stiffness, they are viscous, it's rate dependent. And so if I do a test at a slow strain rate, I get a certain strength. If I do a test on exactly the same soil, at exactly the same state and confining pressure at a very fast rate, I get an increase in strength. And sort of a rule of thumb is that for every log increase in strain rate, for every increase in strain rate by a factor of 10, I get a 10% increase in the strength of the soil. It can be 5%, it can be 20%, it depends on the nature of the soil. We tend to think that the strain rate increases are log linear. If you do multiple tests very carefully, you'll actually see, just like almost everything we have is nonlinear, but we often use linear extrapolations to underestimate the strength, but realize sometimes when it comes to site response, underestimating strength can be unconservative, and so you should do your best estimate of what you think is the peak dynamic strength at a strain rate reflective of what you might get during an earthquake. What that typically leads to is taking your peak static strength that you get in a conventional laboratory test and multiplying it by a factor of something like 1.3 to 1.6. And many times it's around 1.4. But that's one cycle of loading. What happens when you cycle the soil back and forth? Each cycle generates a little bit of pore pressure and a little bit of softening, which we call degradation. And so if we cycle a sample, let's say 6 times, keep the specimen undrained, and then do a static test, we'll end up that the post-cyclic strength is maybe 15% less than what it was for the first cycle. So you have strain rate effects increasing the strength of the soil when you do a rapid loading, but multiple cycles of those fast loadings will lead to a degradation, and they're competing against each other. The more cycles of loading, the more degradation. You also have progressive failure. If I do a small laboratory test, and one of the smallest laboratory tests is a miniature vein in a clay, I will get a peak strength, and then it will drop down to a residual, and then maybe a fully remolded, and I get a really large number of turns in my vein. If I take exactly the same material, and I make my vein larger, it will come up to a peak strength, but that strength will be less than it was with the small vein, but then it will eventually drop down to the same strength. If I do a shear box test, which is now 30 centimeters by 30 centimeters, of the same material I have done these 2 vein tests, I will actually have it come up and reach a strength that's lower than the other 2, and then drop down to the same strength. That's because you could think about this large test. At some point when I'm loading this element has felt the box moving into it, so it went up to its peak and dropped down toward residual. At the same time, the soil element yellow has actually gone up to the peak and is just starting to drop down. Because of the compressibility of the material, the white dot hasn't even come up to the peak strength yet. A strain softening material along a failure plane in a landslide doesn't achieve the peak strength at exactly the same time. The bad of this is that the actual strength we get from conventional field and laboratory tests is too high. And we should, for a strain softening material, use a strength that's less than that. The good thing is when we do these tests on these small specimens, the soil looks a lot more brittle than in reality. There's a smearing effect that makes the soil less strong, but also more ductile. Earthquake engineering, we love ductility. Last but not least is when we do, for example, a sliding block analysis, this block is not rigid. If it was rigid, we would just look at slip along a distinct failure surface. This is a clay box test done at Berkeley on the shaking table. We use what I ate for lunch, spaghetti, as inclinometers. You can see the slide plane here, and you can see the distinct movement of this earth mass on top of this earth mass. But because this is not a rigid mass, you will get stress cycles that are less than that necessary to fail it, that will cause some distributed shear. And so the difference between the movement at the top and the movement at the bottom of the sliding mass is deformation from shear strain cycles that lead to not failure, but deformation, and hence I call that distributed shear deformation. So you focus on coming up with your best estimate of the peak static strength, and then you adjust it by these factors that are typically less than 1, except for the rate of loading, which is greater than 1. In many cases, what you end up with is 1.4 as a rate effect, 0.85 as a cyclic degradation effect, 0.9, wait, I got the same strength. That's often what you come up, but it depends. A soil that has a static strength has different dynamic peak strengths depending on the earthquake loading. If I take a clay and I get a static strength, if I take that same clay and put it in the lab and run it one cycle really fast, its dynamic strength is higher. If I run it many cycles lower than the peak strength, where I get a lot of cyclic degradation, it's going to be lower. So if I had a near fault pulse motion, I get the rate effect. You see the 1.4 in here. But because it's only one pulse, I really am not getting the cyclic degradation issue. I said the soil wasn't that strain softening. So I could use 1.25 times the peak static strength for the dynamic strength of that clay when it's being excited by a near fault pulse motion. But another ground motion in my suite of ground motions might be an ordinary ground motion from a magnitude 9 subduction zone earthquake. In that case, I get the rate effect of 1.4, but because I have so many cycles of loading, I get significant cyclic degradation, and the cyclic degradation factor might be 0.7. And now I end up with a peak dynamic strength that's 80% of the peak static strength. It is correct and it is consistent to use different peak dynamic strengths for the same soil because it depends on the earthquake loading. That's the peak strength. We often have problems that don't calculate just a couple of centimeters to maybe at most 15 to 30 centimeters, but sometimes we get so much deformation that we're heading down beyond peak, post-peak, to residual, to a large slide, we might get to fully remolded strength. So realize that we're going to talk about a parameter called a yield coefficient, which is a slope stability value that is a function of the strength of the soil. We might use a yield coefficient that's a function of the peak dynamic strength for a certain displacement range. Then we might use a degrading yield coefficient, and eventually, when we get to fully remolded deformation levels, we'll use a KY that's a function of the fully remolded shear strength. Your properties of the soil have to be a function of the deformation. If you're calculating 3 meters of movement, you cannot be using peak dynamic strength for a softening material. So you might do the analysis with fully remolded strengths, and then you'll calculate 9 meters of movement. We often use geosynthetics in geotechnical systems. There's very few tests done on dynamics properties of geosynthetics. So we did this testing with Dr. Kim, who's now a professor in Korea, and our laboratory director, Dr. Reamer. And one of the issues is, do you have pre-shearing or not? If you take a material that has geotextiles in it, like a geofabric, and you rub it back and forth, you'll actually get a reduction in the interface strength. If you have interfaces that don't have geotextiles that polish the interface, pre-shearing can actually cause an increase in the initial strength. So with interfaces, just realize you want to test the interface for the conditions that you think will likely happen. Interfaces, for example, just because the material drags down on it, it can undergo some pre-shearing, and there are cases where pre-shearing will cause the strength to be lower, sometimes higher. It shouldn't surprise us that geosynthetics that are made out of plastic would exhibit some viscosity or strain rate effects, and we do see that. This is tests done on high-density polyethylene with a geotextile, and you can see as you increase the rate of loading, the strength, the peak strength increases. But this is largely, this increase in friction angle with strain rate is largely for dry interfaces. When we did these same tests under saturated conditions, we did not see that strain rate effect. A major caveat to this is these are difficult tests to run, so we could only run them under low normal stresses. These are appropriate for interpreting interfaces at low confining pressures, but if you have high confining pressures, you need to think about that. So in conclusion, the key to understanding soil response is understanding its volumetric strain response tendencies during drain shear. Anyone who develops a constituent model starts with understanding the volumetric strain tendency of the soil, then they use a flow rule to then figure out the deviatoric strain. It's the volumetric strain that tells us all the really important things, because during undrained loading, it tells us about pore pressures, which change effective stress, which changes stiffness and strength. Soil density, confining stress, fabric, stress history, largely determine soil response, because it largely determines its volumetric strain tendencies. And then for clays, we realize we really want to focus on understanding the static, undrained shear strength of that clay. And that's a major challenge. Once we have that figured out, we want to focus on dynamic effects. And two of the most important are the competing effects of increase in dynamic peak strength because of strain rate and loss of strength because of cyclic degradation. And therefore, you want to choose a strength, peak dynamic strength of clay that is a function of the loading, and every earthquake motion imparts a different type of loading in terms of equivalent number of cycles of loading as well as its rate of loading. And then also think about post-peak drop in strength if that's important. Thank you very much. Any questions while Professor Kramer comes up? I see head scratching. So you have internal questions.